Raptor 2 engines are being scrapped this year, and Elon Musk finally reveals why. The explosion at SpaceX's Ship 35 static fire test wasn't just an anomaly, it exposed fundamental flaws in the engine's design that SpaceX can no longer ignore. While Musk initially promised Raptor 2 would revolutionize space travel, 3 failed launches and a catastrophic vacuum engine explosion tell a different story. What went so catastrophically wrong? The shocking truth. Raptor 3 was already being quietly developed as the emergency fix, with 21% more thrust, better cooling systems, and zero bolted joints. Is this SpaceX's most critical engineering pivot yet? Let's dive right in. When Elon Musk unveiled Raptor 2 in February 2022, it wasn't just another engine. It was supposed to be SpaceX's golden ticket to Mars. Standing proudly on stage, Musk presented what seemed like an engineering marvel: sleeker design, simplified manufacturing, and most importantly, raw power that dwarfed its predecessor. On paper, Raptor 2 was perfect. In reality, it became SpaceX's most challenging puzzle yet. "This engine will revolutionize access to space," Musk declared back then. But fast forward to 2025, and that revolution has been more about learning harsh lessons than celebrating victories. What exactly went wrong with the engine that was supposed to change everything? Let's break down the evidence. During Starship's first flight, 3 Raptor engines failed to ignite before liftoff. Think about that. The most advanced rocket engine on Earth couldn't even start properly. Starship lifted off with just 30 of 33 engines running. Then 27 seconds into flight, something SpaceX engineers cryptically called an energetic event knocked out several more engines. But what does energetic event actually mean? In aerospace engineering terms, it's code for something exploded that wasn't supposed to. This cascade failure left mankind's most powerful rocket spinning uncontrollably through the atmosphere. Flight 2 seemed promising at first. All 33 engines fired perfectly at liftoff. But the success was short-lived. At 2 minutes and 55 seconds after stage separation, when Super Heavy attempted to flip around for its boost backburn, multiple Raptor engines refused to reignite. The result? Another flight termination. Wait, notice the pattern forming? The Raptors work fine at initial ignition, but fail during reignition attempts in flight. Why would this happen? The answer lies in a critical design change that most space enthusiasts completely missed. Raptor 1 used a reliable torch igniter inside the main combustion chamber, essentially a small rocket that lights the big rocket. But Raptor 2? SpaceX completely abandoned this proven approach. To this day, Musk hasn't revealed exactly what ignition system replaced it. Imagine removing the spark plugs from your car and replacing them with something else, something unproven. That's essentially what happened with Raptor 2. What makes this particularly dangerous is the full flow stage combustion cycle that Raptor uses. Unlike conventional rocket engines, Raptor needs successful ignition at 3 critical points simultaneously: the fuel side preburner, the oxidizer side preburner, and the main combustion chamber. If any one of these fails to ignite properly, you're not dealing with a simple misfire, you're facing a potential bomb. Liquid oxygen and methane don't just sit there when they mix without igniting. They create one of the most volatile combinations imaginable. After Flight 7's failure, SpaceX promised an upgraded ignition system. But then came Flight 8, where not 1 but 2 engines failed during boostback reignition. The fix clearly wasn't fixing anything. But that's just the beginning of Raptor 2's troubles. During recent flights, Starship's upper stage engines encountered something engineers fear more than almost anything else: unexpected harmonic resonance. Think of it like this. Imagine a wine glass shattering when a singer hits just the right note. That's harmonic resonance. Vibrations that match an object's natural frequency, amplifying until something breaks. In Starship's case, these vibrations were attacking the most vulnerable parts of the Raptor engines: their powerhead components and propellant feed lines. The result? Critical methane leaks that ignited inside the engine bay, essentially starting fires in one of the worst possible places on a rocket. What's truly concerning is that these resonance issues never appeared during ground testing. They only emerged in actual flight conditions. This suggests that something fundamental changed between Starship's testing environment and its flight configuration. The most likely culprit, structural modifications in the new Starship Block 2 design, particularly in how the propellant plumbing is arranged. And then came the most alarming incident yet. Just last week, during what should have been a routine static fire test with Ship 35, disaster struck. One of the Raptor 2 vacuum engines, specifically designed for optimal performance in space, catastrophically failed mere seconds after the propellant system activated. Witnesses described a sudden eruption of flames from the base of the ship, followed by a massive cloud of smoke that engulfed the Massey test site. The likely cause? Uncontrolled fuel leaking from the engine's plumbing, which was then ignited by exhaust from nearby engines. This wasn't just another minor setback, it was a dramatic, public demonstration of Raptor 2's fundamental flaws. Even in the controlled environment of a static fire test, these engines were proving dangerously unreliable. SpaceX has remained conspicuously silent about this particular failure. No press release, no explanatory tweets from Musk, but their actions speak volumes. While SpaceX publicly focuses on fixing bugs in Raptor 2, behind the scenes a completely different strategy is unfolding: the rapid development and deployment of Raptor 3. Industry insiders and engineers across social media platforms have reached a surprising consensus. Rather than continuing to patch Raptor 2's inherent flaws, SpaceX should cut their losses and accelerate the transition to Raptor 3. But is Raptor 3 truly the answer, or just Raptor 2's problems in a new package? Consider this. When Apple released iOS 1, it was revolutionary but buggy. The same pattern repeated with Windows 95, PlayStation 1, and virtually every groundbreaking technology. First major redesigns almost always come with unforeseen issues. Raptor 2 represents SpaceX's first major engine redesign, leveraging advanced 3D printing to simplify complex components like pumps and injectors. They stripped away the external pipes, wires, and sensors that made Raptor 1 look like a Christmas tree. But in that simplification process, they may have removed too much, including critical safety redundancies. Raptor 3 appears to correct these mistakes while pushing performance even further. Raptor 3 maintains the same full-flow stage combustion cycle as its predecessors, but with crucial refinements. Picture two powerful rivers, one fuel-rich, one oxygen-rich, that circle around before converging in a controlled explosion. The key innovation in Raptor 3 is its refined cooling system, precisely what Raptor 2 struggled with. It employs regenerative cooling, where super-cold liquid methane circulates through channels built directly into the chamber and nozzle walls. This accomplishes two critical functions simultaneously. It prevents the engine from melting under 3,000 degrees Celsius temperatures while preheating the fuel before combustion, dramatically improving efficiency. But SpaceX didn't stop there. They added a film cooling system where a thin layer of methane creates a protective thermal barrier inside the combustion chamber, especially around high-stress areas like the nozzle throat. This prevents the overheating, deformation, and dangerous fuel leaks that plagued Raptor 2. Musk himself confirmed these changes on social media, stating, "All the small plumbing and wiring had to be deleted or incorporated into the primary structure because Raptor 3 will have no heat shield. Also, all parts have to be actively cooled." Perhaps the most significant upgrade? The complete elimination of bolted joints in favor of welded connections. While bolts allow for easy assembly and maintenance, they're vulnerable to extreme heat and pressure. Welds offer greater reliability, reduced weight, lower complexity, improved thermal performance, and decreased production costs. This change alone could solve the harmonic resonance issues that have haunted Raptor 2. If design improvements aren't convincing enough, the raw performance numbers tell a dramatic story. Raptor 3 generates 280 tons of thrust at sea level, a staggering 21% increase over Raptor 2's 230 tons. Despite this power increase, it's actually lighter, 1,525 kilograms compared to Raptor 2's 1,630 kilograms. With a specific impulse of 350 seconds, Raptor 3 delivers better efficiency in every operating condition. These aren't minor incremental improvements. They're game-changing advances that could fundamentally alter Starship's capabilities. How did SpaceX achieve these seemingly impossible improvements? By eliminating unnecessary components and integrating others directly into the engine structure. The countless bolted joints in Raptor 2 have been replaced with single-piece welded structures in Raptor 3, dramatically simplifying production while improving reliability. The trade-off? Maintenance becomes more challenging since some components are now permanently integrated beneath welds. But in the context of a rapidly reusable launch system, reliability trumps maintainability every time. A leaked photo from late last month appears to show a Raptor 3 engine being transported at SpaceX's McGregor test facility. This suggests SpaceX isn't just developing Raptor 3 for some distant future iteration. They're actively preparing to deploy it, and soon. While it's unlikely we'll see Raptor 3 on Flight 9, the rapid pace of development indicates we may not have to wait much longer. SpaceX has already replaced the failed Raptor vacuum engine on Ship 35 with another static fire test expected as early as next week. More significantly, maritime warnings have been issued for S-35's landing zone in the Indian Ocean, covering May 9th to May 22nd. The most likely launch date? May 20th based on current preparations. The question now becomes, how many more flights will Raptor 2 power before SpaceX makes the inevitable switch to Raptor 3? And with SpaceX's second launch pad expected to be operational by year's end, could we soon see multiple Starship launches per week? Potentially some powered by Raptor 2 and others by Raptor 3? One thing is certain, SpaceX isn't following the traditional aerospace playbook of perfecting each component before moving forward. Instead, they're embracing rapid iteration, learning from failures, and constantly pushing the boundaries of what's possible. It's a strategy that's proven successful with the Falcon 9, but Starship represents an entirely different scale of challenge. Raptor 2's struggles reveal something profound about SpaceX's approach to innovation. While traditional aerospace companies might view these failures as setbacks, Musk sees them as stepping stones. From the ashes of Ship 35's explosion, Raptor 3 emerges not as a contingency plan, but as the next deliberate step in SpaceX's Mars roadmap. This isn't just about fixing an engine. It's about fundamentally changing how humanity approaches space travel. With each failure, each explosion, each redesign, we're watching the real-time evolution of technology that will eventually carry humans to another planet. The question isn't whether SpaceX will overcome these challenges, it's how soon. Will Raptor 3 be the final iteration or merely another step in the journey? How many more versions will we see before humans step onto Martian soil? One thing's certain, the pace of innovation is accelerating. What took NASA decades now takes SpaceX months. Keep your eyes on the skies, especially around May 20th. This next launch could reveal far more about Starship's future than SpaceX is currently willing to admit. And remember, today's explosions are tomorrow's textbooks. That's how humanity reaches the stars. This is Space Core, where we don't just watch history happen, we help you understand it. SpaceX just revealed why they won't use glue on Starship's heat shield, and it's mind-blowing. During re-entry, temperatures hit 2,700 degrees Fahrenheit, hot enough to instantly vaporize any adhesive known to man. So how does SpaceX secure 18,000 critical hexagonal tiles to a massive steel rocket without them ripping away? The engineering challenge seemed impossible. While competitors struggled with complex solutions, Elon Musk's team developed an ingeniously simple mechanical system that shocked even NASA veterans. This isn't just clever engineering. It's the difference between reaching Mars or burning up in Earth's atmosphere. Let's dive right in. When a spacecraft returns to Earth from orbit, it faces one of the most brutal physics challenges in engineering. Starship doesn't just glide back like a plane. It slams into the atmosphere at over 25 times the speed of sound. The friction generates temperatures that would melt almost any material known to mankind. This isn't just hot, says one SpaceX engineer who worked on the project. We're talking about temperatures that would turn your kitchen oven into a popsicle by comparison. At 2,700 degrees Fahrenheit, That's 1,482 degrees Celsius. Steel melts, aluminum vaporizes, and conventional aerospace materials simply disintegrate. This extreme environment creates what engineers call the attachment paradox. The hotter it gets, the more protection you need. But the harder it becomes to keep that protection attached to your vehicle. So why not just use super strong glue? Here's where physics throws the first curveball. Any chemical adhesive would simply burn away long before the vehicle completes re-entry.